Imagine a universe where everything pulls on everything else. That's exactly what Newton's law of universal gravitation is all about. It explains how mass and distance play their roles in the epic gravitational tug-of-war between two bodies, shaping their every interaction. This relationship isn't just some nerdy science stuff, it's crucial for how we understand motion in space.
Pretty cool, right?
Now, here's where it gets even more interesting. The inverse square law comes into play. Picture this: as two masses drift further apart, the gravitational force between them fades away dramatically, which changes how strongly they're drawn to each other. This principle is like the secret sauce in celestial mechanics, helping explain everything from the paths of planets to the dance of galaxies. Let's talk about Newton's first law for a second. It's simple yet powerful: an object in motion stays in motion unless something messes with it.
Think about it.
This is why planets are locked in their orbits around the sun, gliding along in a cosmic ballet. It's all about that delicate balance between inertia and the gravitational pull. Science is like a dance, and this law is one of the core beats. And what about energy? It's like the ultimate shapeshifter in the universe. Energy comes in different forms and can change from one to another, like when you drop your phone and potential energy transforms into kinetic energy as it plummets. This is a perfect example of energy's role in our everyday lives and in all kinds of physical phenomena. Speaking of energy, let's dive into work. Work is all about applying force over distance, like when you lift an apple. Every time you push or pull something, energy is transformed, showcasing the crucial difference between energy and work. This distinction lays the groundwork for understanding physics in a whole new light. Now, hold on to your hats because here comes the conservation of energy. This principle tells us that energy can't just vanish into thin air, it can only change forms. Think about a car slowing down: its kinetic energy is transformed into heat when braking. This is a vital rule that applies to everything we see around us. Let's get a bit more abstract and talk about entropy for a moment. Picture an ice cube melting. It's like watching something orderly change into a wild and chaotic liquid. This is entropy in action, showing how things naturally drift towards disorder. It's a fascinating way to understand the world around us. But wait, there's more. The universe is on a one-way street to higher entropy, and this is linked to how we perceive time moving forward. Think about your favorite movie. Things happen in a sequence, right? This concept helps explain why everything seems to progress in one direction, making sense of the flow of time. In practical terms, this means that low-entropy energy forms, like gasoline, are super effective for doing work, way better than their higher entropy buddies. This has real implications for how we think about energy efficiency in our gadgets, cars, and even in our homes. Now, let's zap into the world of electricity. The first equation we encounter tells us that electric charges create electric fields. These fields can influence other charged particles, which gives us the foundational concept of electrostatics in electromagnetism. Electricity is like a hidden superpower in our world. And speaking of superpowers, the concept of induction shows us how a moving magnet can whip up an electric field. This principle is the magic behind cool tech like wireless charging pads that juice up your devices without any cords. It's like science fiction coming to life. Next up, let's chat about electromagnetic fields. Picture them radiating outward as electric and magnetic fields dance together, creating electromagnetic waves. These waves are everywhere, from visible light to all those frequencies powering your favorite tech. It's a high-tech world, and we're just living in it. Ever heard of half-life? This concept helps us wrap our heads around how isotopes stabilize and decay over time. It's super important in fields like nuclear medicine, where understanding this principle can make a difference between life and death. This science thing? It's got some serious stakes. Now, let's get mind-blowing for a second: Einstein's theory of relativity. This revolutionary idea established that the speed of light is a constant, flipping our traditional ideas about time and space on their heads. It was like a cosmic wake-up call that challenged everything we thought we knew from Newton. Einstein didn't stop there. He proposed that gravity isn't just some invisible force, but rather a result of mass-bending spacetime. It's like a giant trampoline with planets and stars making impressions on it, changing our understanding of how gravity works. This concept is the backbone of many modern astrophysical theories. Can you even imagine? His groundbreaking work didn't just stop with gravity. Einstein's revelation that light behaves like a particle laid the groundwork for quantum mechanics. This unexpected field changed the game completely, reshaping our understanding of energy and the tiniest particles in existence. It's as wild as it sounds. Now, dive into the weirdness of quantum mechanics. The concept of superposition illustrates that particles can exist in multiple states at once. It's like being both awake and asleep at the same time. Until we measure them, it's a mystery. This challenges everything we thought we understood while living in a classical physics world. And don't forget about Heisenberg's uncertainty principle. This mind-bending idea shows that we can't measure both the position and momentum of quantum particles at the same time. It highlights the paradoxes of quantum physics, making it clear that observing subatomic particles is way more complex than we ever imagined. Science is truly a remarkable journey.